All right, in this chapter, we're going to talk about universal gravitation and circular motion. But for today, our conversation will be focusing on this law of universal gravitation. So the idea behind universal gravitation is that we understand that there are 3 of Newton's laws that we just talked about in the last chapter. And the third law said for every force applied, there is an equal and opposite reaction force. And so we talk specifically about how I can press on the wall and the wall pushes back on me. I can have my book sitting on the table. So the book pushes down on the table pushes up on the book. So those are the very clear and obvious examples of Newton's third law where we have direct contact forces. Then we began talking about some of those field forces, such as gravity, where we had a force of gravity pulling down on an object. So if I have an apple hanging on a tree, then there is a force of gravity down on the apple exerted by the earth. And so the responding force would be that there is a force upward on the earth exerted by the apple, right? Equal and opposite forces. So when we start thinking about this law, we can think about how this law might pertain to objects not only within Earth's atmosphere, but outside of Earth's atmosphere. And so this law is called Newton's Law of Universal Gravitation. So not only does this action-reaction force concept take place here on Earth, but if we were to stop and think about what is it that causes the moon to stay in orbit around the Earth? Why does the moon not fly off and drift into outer space? Well, if the Earth has a gravitational force, the Earth is exerting a force onto the moon. So if this is our moon, then the Earth applies a force onto the moon, and in response to that, the moon is going to apply a force back onto the Earth. Now we can see this, we can see evidence of this with the waves that we have. So we have seasons of high tide where we have really large waves and low tides where we have much smaller waves. And if you look at the arrangement of the moon in its relation to the Earth, the times of the year where we have those really large, massive waves are going to be the times of the year where our moon is located at a distance closer to the Earth than other times of the year. So that equal and opposite force is evident here. As the moon pulls on the Earth, we can see the movement of the water. And so whenever we start to think a little bit deeper about this relationship, then we begin to understand that it's not only the distance between those two objects that's going to affect how weak or strong that gravitational force is, but it's also the mass of those objects. So when we talk about Newton's law of universal gravitation, we need to consider how massive are our objects. So if we were in the classroom, and let's say that I had 2 students and they were standing side by side, okay, or they are standing close to each other. We're social distancing, right? So let's say that they are standing 6 feet apart, okay? So if we have these 2 students in the classroom, there is actually a gravitational force between them. This gravitational force is an attractive force because student A is going to apply a force onto student B towards them, and then student B is going to apply a force onto student A so that it pulls towards student A. So what we have is that both of these forces are pulling these objects together, right? This is an attractive force. If I know that the force being applied onto student B is 50 newtons, then I also know that the force being applied onto student A is 50 newtons. This is a shared force. So when we look at our formula here in just a moment, we're going to see that there's only one F for force because it's the same force value for both of our objects. Now, if we were physically present here in the classroom, these 2 students that are 6 feet apart are going to experience a gravitational force between them. However, they are not going to create a force strong enough to cause the other student to accelerate, right? We need to have a large enough mass in order to create a strong enough force. But in theory, how massive my object is, so what is the mass of object A or object 1? What is the mass of object B or object 2? The size or the mass, the amount of mass for these two objects is going to influence its ability or the strength of the force, which then creates the ability for it to cause a change in motion in other objects. So when we think about the mass of the Earth and the mass of the moon, these are definitely much more massive objects. So because of their extremely large masses, they are able to create a gravitational force that can actually affect other things, okay? What is the other factor that's going to affect the strength of this force? Well, it's the distance between them. How close are these objects? If we take our two students who are currently social distancing and they are 6 feet apart, and we move them so that now they are breaking the rules, and they are closer together, and let's say now they're only 1 foot apart. Well, these students are going to once again create a gravitational force between the two of them. The strength of that gravitational force, though, is now greater because they have put less space between them, because they have increased the distance between them. They have now caused the strength of that force to increase. So this force value is now going to be some value larger than the original 50 newtons because they are closer. If for some reason the moon moved closer to the Earth, then that gravitational force is going to be greater, and that's what we see when we have those seasons of high tides, when the moon's orbit brings it closer to the Earth. So what is that formula? Here is your formula. Fg is equal to capital G times m1 times m2, and all of that is divided by the radius. So let's make sure that you understand what these different symbols mean. Capital F is obviously for force, and this is going to be measured in newtons. That has not changed. Lowercase m is going to be for the mass of the object, and we want this to be in kilograms. If it is not, you will need to convert. We have an M1 and an M2 because we have two different objects. It doesn't matter if we were calculating for the moon and the Earth. It doesn't matter if I put the Earth in place of M1 or if I put it in place of M2, just as long as I have both of those objects accounted for in my formula, okay? R stands for the radius. And so in our scenarios that we've discussed so far, I've just been using the term distance, or how far apart they are. So the radius is going to serve as our distance, or our how far, and so that will be measured in meters. Once again, if it's not given to you in meters, please make sure that you convert that. So if we have the Earth and then we have the moon, we know that the moon is going to follow, let's for argument's sake, say a circular pattern around the Earth. So at any given time, the center of the Earth compared to the center of the moon, the center of the Earth and the center of the moon are some distance apart, right? Well, if I look at the moon's orbital path, that's a circle. This is essentially the radius of the circle. So whenever we're talking about things that are orbiting, something that's circling another object, that radius is going to serve as the distance. For some of the questions you're going to see, they might give it to you as a radius, as long as you comprehend that this is an object moving in a circular pattern, and the center of that circle is point A, and then the center of your object is point B, then that radius would indeed serve as your distance. If it's some different scenario, then you'll have to analyze the situation and then make the interpretation for yourself if you need to do anything different to get that radius value, okay? And then the last variable that we have not identified yet is this capital letter G. So this capital G stands for the universal gravitational constant. And this is just that. It is a constant. It is a set value that you will use in every calculation. And here is what that value is. 6.67 times 10 to the negative 11 is the value that you will use in any calculation where you are determining a force in newtons, a mass in kilograms, a radius in meters, okay? And you can see that we've provided the units here. It's a Newton meter squared divided by kilogram squared. Basically, if we were to do some simplification with our units, we would see that these units would cancel out and we would be left with newtons, okay? So how are we going to go about putting this information into our calculators? Well, if we were in class, I would have you guys take out your calculator and then I would ask you to go ahead and actually calculate this answer. I would like for you, if you have not done this yet, I would like for you to do this. So I skipped over the word problems and I just simply wanted you to see here is how all the numbers plug in if I went through the whole guess process and put my formula together. Can you correctly type this in your calculator so that you get the correct answer? Many times when students are typing numbers in scientific notation in their calculators, they like to punch in 6.67 and then they want to hit that multiplication sign and then they hit the number 1 and then they hit the number 0 and then they hit this caret button so that now they have to put in the the values for their exponent and it's in that little superscript box. If you're choosing to enter your numbers this way, please put it in parentheses so that your calculator knows that this is one value to be considered in the math work. I would prefer that you guys use your E button. So the way it will look on your calculator screen is like this. That letter E is going to take the place of the times 10 caret. Okay, so I would type 6.67, I would hit my E button, and then I would hit negative 11. Okay, so it saves me some buttons to push, and I don't have to put it in parentheses because the calculator recognizes what this number is, and it's just one value expressed in scientific notation. If you don't know what that E button is, it's usually the second function on your calculator, and it's going to be a double E on your calculator button, okay? All right. So if you type this into your calculator, what you should get is a number that comes out to be something close to 4.16 something times 10 to the negative 24. So my final answer here would be 4.2 times 10 to the negative 24. If you did not calculate this when you punched it in, please see me and allow me to assist you with how you are typing this into your calculator, because obviously the problem has been set up for you. So that's not the issue. It's just how you're typing it in. Please make sure that you understand how to correctly enter this so your calculator does what you want, okay? All right, let's look at the last little bit of information I have here on this slide. How do changes to these variables affect the gravitational force value? So if we ask you conceptually to look at this equation, Fg equals gmm over r squared, if I am asking you to change your mass, so let's say that we are going to take our mass of one of our objects and we're going to double it. So something crazy happens and the mass of the moon now doubles, okay? What we would do is we would take whatever the value is for the mass of the moon and we would multiply that by the number 2. So if I keep all of the numbers the same as the original, but I simply take one variable and multiply it by 2, I'm doubling my answer, right? So we would say that our force would also be doubled. So if I have doubling the mass creates double the force, then that's going to give me a direct relationship between mass and force. So doubling my mass is going to give me double the force. They're both going to increase together. If I were to take the mass of the moon, let's say there was some sort of event where we lost a portion of the moon, if the mass of the moon decreased, then that gravitational force value would decrease, okay? If we were to look at how changing the radius affects our force, now it is going to be an inverse relationship, and then notice that it says we have to square that value. So it's an inverse square relationship. Inverse square. So if we are going to take our radius, and let's say that we're going to cut our radius in half. If the value for G doesn't change, it can be represented as a 1. It's the same as the original number. And each of our masses don't change, so they're essentially a 1. It's the same as the original setup. But we're going to take our radius and we're going to double that. I don't remember what I said before, but let's say if we double it, then we would be multiplying the original number 1 times 2. So I would put a 2 here in my denominator. And then the formula says that I need to square that. So this is going to simplify to 1 over 4, which means doubling my radius not only decreases my force value because it's giving me a fraction for my final answer here, but it's going to take that and it's going to square the effects. So instead of cutting it in half, it's going to be 1/4 of the original force value. So how would we express that as an answer? We might write it as 1/4 F. We might want to say F over 4. We might say 1/4 of the original, which would be the original force value. So that's the idea behind how we would go about answering questions about changing the variables and how that affects our force. How would the forces compare without necessarily having to perform a calculation? And you will be expected to answer both types of problems.